Look up at the night sky. It's a breathtaking tapestry of twinkling stars. Each pinprick of light is a distant sun. Have you ever wondered, how far away are they? It's a question that has captivated astronomers for centuries. Measuring the vast distances to stars and galaxies is no easy feat. Join me on a journey to explore the fascinating world of cosmic cartography. Imagine you're driving down the road and you pass a tree. Notice how the tree seems to move quickly across your field of view? Now look at the mountains in the distance. They appear to move much slower, right? This phenomenon, called parallax, is a powerful tool for measuring distances. In astronomy, we use the same principle. As Earth orbits the Sun, our perspective of nearby stars changes slightly against the backdrop of more distant stars. This shift in position is incredibly small but measurable. By observing a star from two different points in Earth's orbit, 6 months apart, astronomers can create a triangle with the star at its apex. Using trigonometry, they can then calculate the distance to the star. The smaller the shift in the star's position, the parallax angle, the farther away it is, just like the distant mountains appearing to move slower than the nearby tree. This method, known as stellar parallax, is our most direct way of measuring distances to stars within a few hundred light-years of Earth. However, as we venture farther into the cosmos, parallax becomes less effective. The tiny shifts in position become too small to measure accurately. That's where other methods like spectroscopic parallax come into play. Just like our fingerprints, every star emits light with a unique spectral signature. Think of a prism splitting sunlight into a rainbow. Stars are like giant cosmic prisms, and their light reveals crucial information about their temperature, composition, and even their distance. Imagine two cars approaching you at night, both with their headlights on. You can easily distinguish the dimmer car from the brighter one, right? Similarly, astronomers can use the spectrum of a star to determine its intrinsic brightness, also known as its absolute magnitude. Once they know a star's absolute magnitude, they can compare it to its apparent magnitude, which is how bright it appears from Earth. The difference between these two magnitudes tells us the distance to the star. This method, known as spectroscopic parallax, allows astronomers to estimate distances to stars thousands of light-years away. But what about even greater distances, where even spectroscopic parallax becomes unreliable? Enter the realm of cosmic lighthouses, Cepheid variable stars. Section 4. Cosmic lighthouses, Cepheid variables and the expanding universe. Some stars pulsate, rhythmically brightening and dimming over a specific period. Among these pulsating stars are Cepheid variables, named after the first such star discovered, Delta Cepheid. These stars are special because their pulsation period is directly related to their intrinsic brightness. Imagine, if you will, a lighthouse with a powerful beam of light. The closer you are to the lighthouse, the brighter the light appears. Similarly, astronomers can determine the intrinsic brightness of a Cepheid variable by measuring its pulsation period. By comparing the Cepheid's intrinsic brightness to its apparent brightness, they can calculate its distance. This method has been instrumental in measuring distances to nearby galaxies millions of light-years away. In fact, it was observations of Cepheid variables that led astronomer Edwin Hubble to his groundbreaking discovery of the expanding universe. Section 5. Galactic spin. Doctors unveiling distance through rotation. As we venture even farther into the cosmos, we need even more powerful tools to measure distances. One such tool is the Tully-Fisher relation, which links the rotational speed of a spiral galaxy to its intrinsic brightness. Imagine a spinning figure skater. As they pull their arms closer to their body, they spin faster. Similarly, spiral galaxies with more mass rotate faster. The Tully-Fisher relation allows astronomers to estimate the mass of a galaxy by measuring its rotational speed. Once they know the galaxy's mass, they can infer its intrinsic brightness, as more massive galaxies tend to be brighter. By comparing the galaxy's intrinsic brightness to its apparent brightness, they can then calculate its distance. This method is particularly useful for measuring distances to galaxies within a few 100 million light-years. But what about the most distant objects in the universe, billions of light-years away? For those, we turn to the spectacular explosions of Type Ia supernovae. Section 6. Cosmic fireworks, supernovae as standard candles. Type Ia supernovae are cataclysmic explosions that occur when a white dwarf star reaches a critical mass and explodes. These explosions are incredibly bright, briefly outshining entire galaxies. What makes them particularly useful for cosmic distance measurements is that they all have roughly the same intrinsic brightness. Imagine a box of identical fireworks. If you set off one firework at a known distance and measure its brightness, you can then determine the distances to other fireworks by comparing their apparent brightness. Type Ia supernovae act as cosmic fireworks, providing astronomers with standard candles to measure vast distances. By observing Type Ia supernovae in distant galaxies and comparing their apparent brightness to the known intrinsic brightness, astronomers can calculate the distances to those galaxies. This method has been crucial in mapping the large-scale structure of the universe and understanding its expansion history. Section 7. A Universe Measured. Reflections on the Cosmic Distance Ladder. From the subtle shifts of nearby stars to the brilliant explosions of distant supernovae, astronomers have developed a remarkable arsenal of tools to measure cosmic distances. Each method has its limitations, but together they form a cosmic distance ladder, allowing us to chart the universe from our cosmic backyard to the edge of the observable universe. As we continue to explore the cosmos, we refine our measurements and develop new techniques to push the boundaries of our cosmic understanding. The quest to measure the universe is a testament to human curiosity and ingenuity, a journey that began with stargazing and has led us to the very frontiers of knowledge. So, the next time you look up at the night sky, take a moment to appreciate the vast distances involved and the incredible methods we use to measure them. Which method do you find the most fascinating? The subtle dance of parallax? The spectral fingerprints of stars? Or perhaps the cosmic fireworks of supernovae? The universe is full of wonders, waiting to be discovered, one light year at a time.